Hello, good evening. This is Professor Khan. This is week 5, combustion control circuit, EST-101. And this week we will follow up with some more control about ignition system. We did some work with ignition last semester, and we did adjust the electrodes. We also went through some hands-on into testing a transformer. So this will be some sort of a revision and also addition to how does this contribute into the control. And we will do some wiring on the board to see, to calculate the timing for the ignition and when does the system drop the ignition. Okay, let's start. Hold on. Okay, so first we would like to identify two types of ignitions. There are two types now of ignition, not igniters, ignition. We have something called constant ignition and constant, which also known as intermittent ignition. And we also have interrupted ignition, and that is called uh, non-constant. These are the two types of ignition. Some of the old boiler will have constant ignition, especially for oil, and that is not a very good idea, especially when it comes to energy conservation. We'll also, okay, so we will list the ignition system components, what is it composed of, what goes in it, and that's for oil. I will also post a video about gas ignition systems. Again, gas ignite faster than oil. We'll explain how troubleshoot ignition system, what could be the problem with ignition systems. It can be very frustrating if you don't have the right ignition. That could be very problematic because the system will not ignite and it will go in trial for 3 times. We did say that the trial for ignition now is 15 seconds for ignition is 15 seconds. It used to be 45, then 30, now it's 15 seconds because we do have the means to shut off the system in 15 seconds, and we are supposed to be able to recognize and see flame in 15 seconds. Some of the issues that will happen with delayed ignition as well, we'll try to address. So the ignition system, again, if you go into industrial boilers or commercial boilers or residential, they will always have the same components. We will have our electrodes here, which make the spark between them. The spark is basically a 10,000 volt jumping through those electrodes through airs. And we said air is conductive at 10,000 volts. And these has to connect to ignition transformer. We have to make this voltage that goes through this electrodes. And anytime we have any kind of leak of this voltage, we might not have the proper ignition. It's very important to have this setup at the right distance from the plate, the right distance from each other, and the right distance from the nozzle itself. Otherwise, we will lose the power of voltage and spark, which generate heat that is hot enough to ignite the oil. Okay, that being said, interrupted ignition, which it does stop once you see the flame, not you, the cat cell will see the flame or any kind of device that will sense the flame, it will shut off the ignition. And we have the intermittent, which stays the entire time where the boiler is running. Transformers that are still being used for a lot of burners like Beckett's and Carlins. It depends. I personally find them very reliable, but some burners like Rielos, they actually have igniters, which is electronic, and they work in DC and they do the job perfectly. So it depends on the strategy and the way they want to produce the ignition. So this is how transformer work, and probably you've seen them before. We did test the transformers. If you work with Beckett's and Carlin, chances are you'll find a transformer, especially if you work with large boilers, you will have some transformers as well. So they work with electromagnetism, and they have an iron core and copper. That's why they're very heavy. They transfer 120 volts to 10,000 volts. Electronic transformers, actually, they are solid state, and some of them actually work with DC, and they can produce from 14 to 20,000. So they are much stronger. They don't consume as much energy. The problem is some manufacturer found that they break easier, and they don't last as long. So I don't know what is the sales pitch behind it, but it could be either or. And once you have an ignition source, try not to change that ignition source unless you have some approval from the manufacturer. Which is better again? Electro's life. I mean, now I'm comparing which is better. I'm comparing interrupted ignition to constant ignition, and I should highlight that. Igniters or ignition transformer life is significantly reduced when you use constant ignition. Actually, I should change that and fix it right now because I don't like that. Discard. Which is better? Constant or interrupted? Okay. Sorry about that. So electric life is significantly reduced when you use constant, because again, using the ignition the entire time, and the ignition compares a lot to the car spark plugs. So if you use your spark plugs all the time, probably have to change them every 20,000 miles or so. The life of igniters and ignition will be reduced because you're getting more mileage out of it. Electrical consumption is really high when you keep the ignition on. It kind of consumes the same amount as a light bulb that's 150 watts. There's a lot of operation noise, and is increased when you have the ignition on all the time. It will be buzzing the entire time. And also, if you have constant ignition, you will have combustion that will can be like not as clean as it's supposed to, and it will be covered up by constant source of heat to light up the oil at not the optimum conditions. You can produce more nitrogen oxide using constant ignition. Okay, transformers, this is again what they look like, and these are the components, and this is how they produce the arc. Few facts about transformers: they are tire insulated, so there is a possible melt, and they should not be located outside. They are very susceptible to moisture. They have a high electrical consumption from 100 to 150 watt light bulb. They degrade over time. They never last forever. So even though sometimes they work, we have to test them to know they are producing the right power. How do you test them? This is one of the first way to test it is like having a proper designated tester that will be able to measure 10,000 volts. Never ever use a multimeter, because a multimeter voltage limit is 600 volts. Use a tester. You can also test the resistance between the primary and the secondary winding. So you can test the resistance across the primary. First, unplug it. Then what you do is you test the primary. Which says the primary? This is the primary. So you're going to test the resistance for the primary, and it should be 3 ohms. So it's very small. Plus or minus 10% is okay. Then you can test the secondary, and it should be 12,000 ohms in here. And again, make sure it's unplugged, otherwise you're going to have an issue. Solid state igniters, they're really hard to test. They either work or they don't, so you just change them completely. There are a lot of tools that help you test them and make sure they have some power. Do not use the idea of getting them closer to each other and trying to bridge them. That might ruin your transformer. They're heat resistance. They have resistance to moisture. They use lower power from 30 to 50 watts. So that makes them a little bit more efficient, and they produce more voltage. However, as I said, there's an ongoing issue with them breaking more often than transformers. Uh, Going back testing a transformer with a different method. This is a way to compare the resistance between each lead and make sure they're not 10% from each other. And all these methods we did try hands-on in Energy System Lab 1, so I hope you remember that. Again, you can also consult the manufacturer. Why are we testing a transformer over and over again? Because a very frustrating issue if you don't get the right voltage. You can hear the buzz, you can see the spark, but it's not hot enough, it's not strong enough to light up the fuel oil. Another way is watching for the spark and watching for the color to change. It's supposed to be blue. If it goes to orange, then it's not good. I don't think this is very reliable way to test it, but you can do the same thing and measure for the amperage draw from one lead in here. So you can put a multimeter and measure the amperage draw from here. And here it is. So you bring them together, you put a meter, either a clip-on ammeter or in-series ammeter, and measure the draw over 5 or 10 minutes and should not drop more than 10%. Okay, how do we, that's about the transformer and the source of energy. What about the spring clips, the bars, the bus bars, and the cables? How do we test them? Most of them are tested visually, and you can look. There are some sophisticated equipment that let you know if there's a crack or leak of voltage. You don't want to have any cracks or fractures on these because they will leak some voltage, and then you will not have the right voltage at the tip. This is an electrical tester, and it's supposed to light up if there's any leak, and you brush it against the electrodes. Electrodes usually are not that expensive, so when in doubt, you can change the electrodes. Just make sure they are the right length and they are the right distance from the diffuser plate and from the nozzle. Setting the gap is very important, and that's one of the issues that you will have if the gap is not set very well. So you want to have clean electrodes, check the connections, check the insulation, then check the gap and make sure it is as recommended by the manufacturer to get the right amount of heat, so you will ignite the oil. So one of the most frustrating issues is not having enough voltage. So the and the issue happens, excuse me, the issue happens is you do the maintenance and you do everything right, it turns on, then you leave the house or the place, and 2 hours later you get a call that it's off again on safety. So if you have a function that is not consistent, that could be very problematic, and that could lead to a lot of oil being residing in the combustion chamber, and that's a problem. So these are some of the components, so you know what are you looking at when you're trying to take apart or look at what could be the problem in this transformer. Some of the troubleshooting charts, and these are excerpts from the NORA book, and they have a lot of those nice charts to try to find what could be the problem. First thing, check the voltage incoming. That's a very big thing because a lot of people do not check that. Make sure you're having 120 voltage AC. You can check the output using special voltmeter. You can check for short circuits inside the ceramic holders. Check that in the closed position, the bus bars are touching where they're supposed to. It might be working, but when you close it, it's be touching partially or incompletely. So these are some of the remedies, and then you might need to replace the primary control relay, because in that case the problem is not with the ignition, the problem is with the relay. Probably it's not engaging when it's supposed to. Because if you watch there's a video regarding the primary control, you realize that the ignition is controlled by the primary, so the primary turns the ignition on and off as needed. More testing. Check the terminals, check the porcelain, check the location, check the gaps, and check the location of the electrodes in comparison to the nozzle and the plate. These charts are available on the NORA book, and also you can look at the PowerPoint later on and read through them. So there's a video, 20-minute video about primary controls and different types of primary controls from Nora video. I will put that in the Blackboard. Also, there's a video about the control from Riello burners, which they are very sophisticated, they're very reliable, they're not very common in this area, but in case you run into one of them, you want to check their function. And again, the basics are the same, just different mechanism. Okay, see you next week, and we will discuss more control stuff in the following week. Thank you.